Welcome to Organic Chemistry's second lesson. In the first video, I wanted to remind you that lithium likes to form his first energy shell, and this last electron that he holds, the third one across from this third proton here on the second energy level, is free for the taking because it's just floating out here outside of this energy shell that stays stable and protected. And as a consequence, when he loses it, he ends up with kind of a +1 charge on the total. And then fluorine over here completed his second energy level, which is bigger. Just notice fluorine here at number 9 protons, only really to get to 10 electrons. It's not that hard. He only needs one more electron. He has 9 protons that might be willing to spread the load out between them. But as a consequence, he'll have a total of a -1 kind of charge on the whole atom, which isn't a big deal compared to their happiness having completed their own energy levels. Lithium dropped down to just a completed energy level 1, and fluorine moved up to complete this energy level 2. They're both happy like that. And this positive and negative attraction between them as a consequence is just like a magnet. It makes them want to be with each other. But they're not sharing their energy per se in the same way as what we're going to talk about today, which are covalent bonds. So let's say I take a hydrogen over here and a hydrogen over here. Yeah, I want to draw that a little bit better, a little bigger. Here's a hydrogen, here's a hydrogen. Now, hydrogen being the first element, of course, is only going to have that first orbital available to use. And he only has one electron here, and maybe his open space for is here, and here, and here, like this. This electron is attracted to the proton in the center of the hydrogen atom. That's all that's there is one proton. But he's also attracted to this proton. It's not like they claim ownership in the same way human beings claim private property, right? Whatever's nearby is what works. And there's not enough to go around here because to complete an energy level, you need 2 electrons to get to the equivalent of a completed first energy level. But what we find is if we bring these hydrogens closer together, and I know you know where we're going with this, but just stay with me for a minute here. If we bring them just the right distance apart, right in here, of course they're still going to be swirling around and doing things. In fact, they're going to be swirling like this and swirling like this. There's going to be a lot of paths an electron can take. But the most equilibrium, the best spot, the one that they want to be at is in the center here. And as a consequence, each hydrogen feels like its energy levels are completed. Hydrogen here feels like he has his second electron and he can complete this first energy level. And it'll actually form, when you look at it on electron microscopes, something more like this. And we would draw it as the electrons being here, but of course they're everywhere in this cloud, everywhere in this cloud. And it's really important to understand that. So you'll notice that this is kind of like 2 soap bubbles popping together and forming a new shape, but they are not like this. It's not 2 spheres that are overlapped in this way anymore. They will redistribute into more of like this egg shape here. That's super important to pay attention to because as we go forward, it's going to need to make sense. I'm going to show you a diagram called an energy curve. And this left and right represents the distance between 2 atoms, and this up and down represents the energy total in the system. Because on the left here, you'll notice where it's very, very high is where atoms are very, very close together. This is close together, this is far apart. And if I put 2 atoms close together like this, and then I just try and overlap their protons and electrons like this, the protons are going to force apart. They're very unhappy in that situation. And the electrons are going to have a lot of problems as a consequence. So it's actually a very high energy area. If you take 2 hydrogens, which were happy right here, this harmonic environment, this beautiful environment, is this low energy space right here, where they're most happy. If you try and force them together tighter than that, they're going to super resist, and that's where this energy here comes from. And you might want that if you want to put them in a super high pressure environment like that. Well, that's something like what the sun could do. So what about when I take them farther apart? Well, that's kind of what this is here. That's what this is over here. It's a little higher energy than if they're bonded together. This is actually lower energy than this here. And the reason for that is these electrons repel each other. They don't want to be bumping knuckles. They're not in a compatible configuration between the two. They tolerate each other. This covalent orbital here is the lowest energy solution, which means that's what nature really wants. That doesn't mean that's what's going to happen, right? That's not how lucky we get. But for today, I want you to remember a couple of things. The first one is that covalent bonds are shared, which you remember from general chemistry. And that this egg shape here is a lot different than the ionic character of a lithium and a fluorine, who have two separate energy shells that are attracted by electrostatics. You'll notice in the hydrogen there's a plus here and a plus here and a minus here and a minus here. This is neutral. There's no plus and minus outside of the shells. It's all within the orbital shells themselves. And then it formed, as a consequence, a different shape than just two separate spheres, didn't it? It formed something that we're going to lead into called valence bond theory. And I guess we'll wait to do that until we get to the next video. If you're trying to do this class the right way, click on the full playlist here, or just go to the next video.